Welcome to Still Science Lab. Tonight, we explore a question that sits quietly at the edge of physics and technology. What happens when a machine begins to compute in ways no classical computer can realistically follow? Not faster in the ordinary sense, not simply a better laptop, a stronger server, or a larger supercomputer. Something different. A machine that uses the strange rules of quantum mechanics, superposition, entanglement, interference, and measurement to process information in a way the digital world was not originally built to face. For decades, quantum computers belonged mostly to the future. They lived in research papers, theoretical proposals, specialized laboratories, and careful demonstrations that only physicists and engineers could fully appreciate. They were fragile, they were noisy, they required extreme control. They seemed powerful in principle, but distant in practice. They were not the kind of machine that could sit beside ordinary computers and replace them. And they still are not that kind of machine. That is important to say clearly. A quantum computer is not a magical supercomputer. It does not solve every problem instantly. It does not make classical computers obsolete. It cannot simply try every answer in the universe at once, in a simple, cinematic way. Most things people use computers for writing, streaming, searching, gaming, storing documents, running ordinary software, are not waiting for quantum machines to take over. But that is not where the threshold lies. The threshold lies in a narrower, more serious place. Quantum computers may eventually solve certain kinds of problems that classical computers cannot handle efficiently or cannot handle within any practical amount of time. Problems in chemistry, materials, science, optimization, simulation, cryptography, complex systems, information itself. They may become tools for modeling nature at the level where nature is already quantum. And if they become stable and powerful enough, they may also challenge parts of the security architecture that protects modern digital civilization. That is where the word dangerous begins to matter. Not because a quantum computer is a doomsday device. Not because one laboratory breakthrough instantly collapses the internet. Not because quantum computing has crossed into science fiction. The danger is more controlled, more technical, and in some ways, more realistic. A dangerous threshold is crossed when a technology moves from being mostly theoretical toward becoming a practical capability. When the question changes from, could this work someday, to how long until this affects real systems. When a machine built from fragile quantum states begins to leave the realm of imagination and enter the world of engineering roadmaps, national strategy, cybersecurity planning, and economic competition, that kind of threshold is quieter than a dramatic explosion, but it can be more important. Because modern civilization is built on computation. Money moves through computation. Hospitals depend on computation. Satellites depend on computation. Power grids, logistics systems, financial markets, communications, defense networks, scientific research, weather models, drug discovery, and personal identity are all tied to information systems. The digital world is not a separate layer from physical life anymore. It is woven into the operation of society, and much of that world assumes certain problems are practically impossible to solve. Not impossible in the absolute sense, just impossible for any realistic classical computer within a useful time frame. Some encryption systems depend on that assumption. They are secure not because no method exists in principle, but because the best-known classical methods would require enormous amounts of time and computing power. The safety of messages, transactions, identities, and stored data often rests on mathematical difficulty. Quantum computing threatens that assumption for certain problems. Not all encryption, not all security, not every password and every database overnight, but some of the public key systems that modern digital life depends on could be vulnerable to a sufficiently powerful, fault-tolerant quantum computer. That machine does not exist at the necessary scale today, but the possibility is real enough that governments, standards, bodies, and security experts are already preparing for a post-quantum world. This is the threshold, not catastrophe. Preparation. The strange thing about quantum computing is that its power comes from the same rules that make it so hard to build. A qubit is not just a classical bit that can be 0 or 1. It is a quantum system whose state can contain a structured combination of possibilities before measurement. Qubits can be entangled, meaning the information in a system can belong to relationships between qubits, not merely to each qubit alone. Quantum interference can amplify the paths that lead toward useful answers and suppress others. That sounds abstract because it is abstract, but abstraction does not mean weakness. Quantum mechanics is one of the most successful frameworks ever created. It explains atoms, semiconductors, lasers, chemistry, magnetic resonance imaging, and the behavior of matter at microscopic scales. It is not speculation. It is the rulebook beneath modern technology. A quantum computer tries to use that rulebook not merely to describe nature, but to compute with it. That is why the idea is powerful. A classical computer represents information in definite states. Its bits are clear. Its operations follow classical logic. It can simulate quantum systems, but as those systems grow more complex, the simulation can become overwhelmingly expensive. Nature does not seem to struggle to be quantum. A molecule does not need a supercomputer to obey quantum mechanics. It simply exists as a quantum system. A quantum computer, if built well enough, may be able to model certain quantum systems more naturally than a classical machine. That could matter for chemistry, for new materials, for catalysts, for batteries, for medicines, for superconductors, for understanding physical processes that are too complex for classical simulation to capture efficiently. This is the hopeful side of the threshold. Quantum computers could become scientific instruments, not just computing devices. They could help researchers explore matter in ways that are currently inaccessible. They could reveal new materials, better chemical processes, and deeper insights into the quantum behavior of nature. But every powerful tool has more than one direction. The same kind of machine that could help simulate molecules may also threaten encryption. The same progress that excites physicists may concern security agencies. The same capability that could accelerate discovery may disrupt systems built on older assumptions. This is why quantum computing feels different from ordinary technological progress. A faster classical computer extends what we already know how to do. A useful quantum computer changes which problems are reachable. That does not happen everywhere. Quantum computers are specialized. Their greatest known advantages apply to certain classes of problems, not all problems. Many tasks will remain better suited to classical machines. Classical computing will not disappear. The future is more likely to be hybrid. Classical systems working alongside quantum processors for particular applications. But even a specialized breakthrough can reshape the world if the specialized problem is important enough. Cryptography is important enough. Material science is important enough. Chemical simulation is important enough. Optimization and strategic modeling may be important enough. This is why researchers, companies, and governments are racing. They are not only counting qubits, they are trying to make qubits reliable. They are trying to reduce errors, extend coherence, improve control, develop error correction, design better algorithms, and connect quantum hardware with classical systems. The raw number of qubits matters, but it is not the whole story. A larger machine full of errors may be less useful than a smaller system with better stability. The true threshold depends on quality, control, correction, and scale. Quantum computers are fragile because quantum states are fragile. A qubit must be isolated enough to preserve its quantum behavior, but controlled enough to compute. It must be protected from noise, but still manipulated precisely. The outside world is constantly trying to measure it, disturb it, and pull it into ordinary classical behavior. Heat, vibration, stray fields, imperfect operations, and environmental interactions can all damage the computation. In a sense, building a quantum computer is an attempt to hold the strangest parts of nature still long enough to make them useful. That is an extraordinary engineering challenge. And progress does not move in a perfectly straight line. Some announcements are important but narrow. Some milestones are impressive but not practical. Some demonstrations show quantum behavior without solving useful real-world problems. Some breakthroughs are overhyped. Others are underestimated because their consequences take years to unfold. This is why the story must be told carefully. Quantum computers have not ended security. They have not solved everything. They are not magic, but they are advancing. And the dangerous threshold is not a single switch flipped overnight. It is a gradual crossing, a movement from theory to device, from device to prototype, from prototype to capability, from capability to consequence. That gradual movement is exactly why it matters now. If we wait until a powerful quantum computer already exists, some systems may be too slow to update. Cryptographic infrastructure is not easy to replace. Banks, hospitals, governments, satellites, archives, identity systems, and long-lived confidential data cannot all be secured instantly. Some information stolen today could be stored and decrypted later if future quantum machines become strong enough. This is sometimes called the harvest now, decrypt later problem. That risk does not require panic, it requires planning. Post-quantum cryptography exists because the scientific and security communities are not waiting passively. New algorithms are being developed and standardized to resist known quantum attacks. Organizations are beginning to inventory vulnerable systems. Migration strategies are being discussed. The world is trying to prepare before the threshold becomes a crisis. That is the responsible way to face a powerful technology. Not fear, not denial, preparation. Still, quantum computing carries a deeper meaning than cybersecurity alone. It marks a new relationship between intelligence and nature. For most of history, humans built tools from classical behavior: levers, wheels, engines, wires, transistors, circuits. Quantum mechanics was always underneath, but the machines we used mostly behaved classically at the level we controlled. Now we are trying to control quantum behavior directly. We are turning superposition into computation, entanglement into a resource, interference into a method, measurement into an output. That is a remarkable shift. It means the rules that once seemed like philosophical puzzles are becoming engineering principles. The same strangeness that made physicists question reality is being built into machines. The danger is not that quantum computers are mysterious. The danger is that they may become practical. A mystery can be admired from a distance. A practical tool enters the world. It changes incentives. It reshapes security. It creates competition. It opens discoveries and vulnerabilities at the same time. That is the nature of a threshold. On one side, quantum computing is mostly a promise. On the other side, it becomes power. And power rarely arrives with perfect certainty. We do not know exactly how fast quantum computers will scale. We do not know which hardware approach will dominate. We do not know which algorithms will matter most. We do not know whether timelines will accelerate or slow. We do not know how quickly industries will adapt, or where the first truly transformative applications will appear. But uncertainty is not the same as safety, and hype is not the same as preparedness. The correct response lies between them. Quantum computers may not change everything tomorrow, but they are serious enough to demand attention now. They may help science understand matter more deeply. They may help design technologies that do not yet exist. They may also expose weaknesses in systems built for a pre-quantum digital age. That is why the threshold feels dangerous. Not because the machine is magic, not because the future is doomed, but because a new kind of capability is forming at the edge of physics, engineering, and information. A capability based on the deepest rules of nature. A capability that may eventually solve problems our current digital world was never built to survive. A quantum computer is not simply a faster computer. That is the first idea to let go. It is tempting to imagine technological progress as a straight line. One machine becomes smaller, then faster, then more powerful. A room-sized computer becomes a desktop. A desktop becomes a laptop. A laptop becomes a phone. A phone becomes a device that can access more information than entire libraries once held. In that familiar story, computing advances by doing the same basic thing more quickly. Quantum computing is different. It does not begin by asking how to make ordinary computation faster at every task. It begins by asking what information means when the machine itself is built from quantum systems. It asks what happens when computation is no longer based only on definite states, but on the deeper rules of superposition, entanglement, interference, and measurement. A classical computer works with bits. A bit is simple in principle. It has a definite state, usually represented as 0 or 1. Every file, every image, every message, every video, every search result, every line of code, every digital transaction is ultimately built from vast patterns of these definite states. Classical computers are astonishingly powerful because they manipulate those states with speed, reliability, and scale. A bit is either this or that. A switch is on or off. A voltage is high or low. A magnetic region points one way or another. The physical details can vary, but the logic is classical. Information is represented in definite units, and operations transform those units according to clear rules. Classical computers can perform billions or trillions of operations. They can simulate weather, render worlds, train artificial intelligence systems, move money, guide aircraft, and connect civilization through networks. But they are still classical machines. They operate with information that, at the logical level, is definite. Quantum computers use qubits. A qubit is not just a bit that is sometimes 0 and sometimes 1. It is not simply a coin spinning in the air, randomly waiting to land. It is a quantum system whose state can contain a structured combination of possible outcomes before measurement. When measured, a qubit gives a definite result, but before measurement, its quantum state carries more subtle information than a classical bit. This is called superposition. The word can be misleading if it is simplified too much. A qubit is not magically doing every possible thing at once in the everyday sense. It is not a tiny computer trying all answers in parallel like a crowd of invisible machines. A superposition is a precise quantum state with rules. It contains possible outcomes with specific relationships between them. Those relationships can evolve, interfere, and become meaningful during computation. The power of quantum computing does not come from chaos. It comes from control. A quantum computer must guide qubits through carefully designed operations so that wrong possibilities tend to cancel out, and useful possibilities become more likely to appear when measured. This is where quantum interference becomes central. Interference is familiar in the world of waves. Two waves can reinforce each other, making a stronger wave. They can also cancel each other, reducing or removing the effect. In quantum mechanics, probability amplitudes can also interfere. The mathematics is different from ordinary water waves, but the guiding idea is useful. Quantum possibilities can combine in ways that strengthen some outcomes and suppress others. A quantum algorithm uses this structure. It does not simply check every answer and hand us the best one by magic. Instead, it arranges quantum operations so that the computation evolves toward a state where the desired answer has a higher chance of being measured. If designed correctly, the useful pattern is amplified. The wrong patterns fade into cancellation. That is very different from ordinary speed. A quantum computer is not powerful because each qubit is just a faster bit. It is powerful because the whole system can process certain kinds of structure in ways classical bits cannot naturally reproduce. Entanglement makes the difference even deeper. When qubits are entangled, the information in the system cannot be fully described by looking at each qubit separately. The relationship between them becomes part of the quantum state. This is one of the strangest features of quantum physics, but also one of its most important resources for computation. In a classical computer, the state of many bits can be described by listing the value of each bit. This one is 0, that one is 1, another is 0. The whole system can be built up from the individual parts. In an entangled quantum system, the full state belongs to the whole. The relationship carries information. This does not allow faster-than-light communication. It does not mean distant qubits send secret messages instantly, but it does mean quantum systems can store and process correlations that are not available to classical systems in the same way. For certain problems, those correlations can be used as computational structure. Superposition gives quantum states a richer space of possibility. Entanglement links qubits into relationships that cannot be reduced to separate parts. Interference allows algorithms to shape probabilities, amplifying useful outcomes and suppressing wrong ones. Measurement turns the quantum process into a definite result. Together, these ideas make quantum computing fundamentally different from classical computing. But different does not mean universally superior. This is where the hype often goes too far. Quantum computers are not automatically better at everything. They will not replace classical computers for ordinary tasks. They will not make every calculation instant. They will not be used to write documents, stream video, or run everyday apps more efficiently than normal machines. In many cases, a classical computer will remain faster, cheaper, easier, and more reliable. Quantum computers matter because there are specific problems where quantum structure may provide a real advantage. One major example is simulating quantum systems themselves. Nature is quantum. Molecules, materials, chemical reactions, superconductors, and atomic systems all obey quantum rules. Classical computers can simulate small quantum systems, but the difficulty grows rapidly as the system becomes more complex. The amount of information needed to describe a large quantum system can become overwhelming. A quantum computer may handle some of these systems more naturally because it is quantum too. This could matter for chemistry, drug discovery, material science, catalysts, batteries, and energy technologies. It could help researchers understand systems that are currently too complex to model accurately with classical methods alone. In this sense, a quantum computer is not just a computer. It is a controlled piece of quantum reality used to study other quantum realities. Another famous application is cryptography. Certain quantum algorithms could, in principle, solve mathematical problems that are extremely hard for classical computers. Some public key encryption systems depend on those problems remaining hard. A sufficiently powerful and reliable quantum computer could threaten those systems. This is one of the reasons quantum computing is taken seriously by governments and cybersecurity experts, even though today's machines are not yet capable of that at the required scale. But the threat depends on scale, error correction, and engineering maturity, not on magic. Quantum computers are fragile, qubits are delicate. Their quantum states can be disrupted by noise, heat, vibration, stray fields, imperfect gates, and unwanted interactions with the environment. This loss of quantum behavior is called decoherence, and it is one of the great obstacles in building useful quantum machines. A quantum computer must preserve quantum information long enough to compute, while also controlling it precisely and eventually measuring it. That is a difficult balance. The machine must be isolated, but not too isolated to operate. It must be protected from noise, but still connected to control systems. It must use quantum strangeness without letting the outside world destroy it too soon. This is why error correction is so important. Classical computers also have errors, but they are relatively easy to manage because classical bits are stable and can be copied. Quantum information cannot be copied freely in the same way. A qubit cannot simply be duplicated perfectly to make backup copies. Quantum error correction must protect fragile information by spreading it across multiple physical qubits in carefully designed ways, without directly measuring and destroying the information being protected. That is one of the central engineering challenges. A useful quantum computer may require many physical qubits to create a smaller number of reliable logical qubits. The raw count of qubits is not enough. Quality matters. Error rates matter. Coherence matters. Connectivity matters. Control matters. A larger, noisy system may be less useful than a smaller, more accurate one. This is another reason quantum computing should be discussed carefully. The field is real and progressing, but not every milestone means immediate practical revolution. Some demonstrations show that a quantum device can perform a narrow task beyond easy classical simulation. That is scientifically important, but it may not yet solve a useful real-world problem. Other systems may be promising but still far from fault-tolerant operation. The road from laboratory achievement to practical capability is long and difficult. Still, the direction matters. Quantum computers are not different because they are simply faster machines. They are different because they use a different physical logic. Classical computers reduce information to definite states and manipulate those states with classical operations. Quantum computers preserve and manipulate quantum states using superposition, entanglement, and interference to transform probability patterns before measurement. The result is not a replacement for all computing, but a new category of computation with unique strengths and serious limitations. That distinction is essential. If we exaggerate quantum computers, we turn them into fantasy. If we dismiss them because they are not magical, we miss their importance. The truth is more interesting. Quantum computers are specialized, fragile, difficult, and potentially transformative for certain problems. They are machines built from the same rules that make atoms stable: photons strange, and particles behave unlike ordinary objects. They bring the quantum world into computation. That is why they feel unsettling. Classical computers helped build the modern information age, but they operate mostly in the language of definite bits. Quantum computers ask what happens when information is processed by systems that do not become definite until measured. Systems whose possibilities can interfere, systems whose parts can be entangled into a whole. They are not just calculating with numbers. They are calculating with the structure of physical possibility. This does not mean they will answer every question. It means they may change which questions can be asked practically. They may help simulate molecules too complex for classical machines. They may alter the future of encryption. They may open new approaches to optimization or physics. They may also remain limited in many areas where classical computing is already excellent. Their power is not universal, but where it applies, it may be profound. Quantum computers are powerful not because they are faster at everything, but because they process certain kinds of information in a fundamentally different way. That difference is the source of both promise and danger. The promise is that we may learn to compute with nature's deepest rules. The danger is that some of our most important digital systems were built before those rules could be turned into practical machines. And now, slowly, carefully, imperfectly, that boundary is beginning to move. The race toward quantum advantage is not a race toward one magical machine. It is slower than that, more technical, more uncertain, and in many ways, more important. Quantum advantage means that a quantum computer performs a specific task faster, more efficiently, or more practically than the best available classical methods for that same task. The phrase sounds dramatic, but it has to be understood carefully. It does not mean a quantum computer becomes better than every classical computer at everything. It does not mean ordinary computers are suddenly obsolete. It does not mean a quantum machine has crossed into unlimited power. It means that for one carefully defined problem, under specific conditions, a quantum system has done something classical systems cannot realistically match. That is the first real threshold, not universal dominance, specific advantage. A classical supercomputer is still an extraordinary machine. It can model weather, train artificial intelligence systems, simulate explosions, analyze genomes, process financial markets, and search through vast data. Classical computing is not weak. It is one of the most successful technologies in human history. The entire digital world was built on it. So quantum advantage is not easy to claim. To matter scientifically, it must compare a quantum device against the best-known classical approaches, not against a weak or outdated method. It must ask whether a classical computer could do the same task with better algorithms, more clever approximations, or more powerful hardware. The comparison is not always simple because classical methods keep improving too. Every quantum milestone challenges classical researchers to find a better way to simulate or compete with it. This makes the race more subtle than headlines suggest. A quantum computer may perform a narrow experimental task that is extremely difficult for classical machines to reproduce. That can be a genuine scientific milestone, but the task may not yet be useful for chemistry, medicine, finance, or encryption. It may be designed mainly to show that the quantum device is entering territory where classical simulation becomes painfully hard. That still matters, because before a technology becomes practical, it often must first become undeniable. Early quantum advantage demonstrations are like footprints near the edge of a new continent. They do not mean cities have been built there. They do not mean industries have already moved in, but they show that the terrain is real. They show that controlled quantum systems can reach computational regimes that classical machines struggle to follow. The question then becomes, can that narrow advantage be turned into useful capability? That is the race. Across the world, companies, universities, national laboratories, and governments are trying to answer it. They are building different kinds of quantum hardware, superconducting circuits, trapped ions, neutral atoms, photonic systems, silicon spin qubits, topological approaches. Each platform has strengths, weaknesses, and unresolved engineering problems. There is no single guaranteed winner. Some approaches are fast but noisy. Some are highly controlled but harder to scale. Some may connect naturally to existing semiconductor manufacturing. Some may offer longer coherence times. Some may be easier to network. Some may be powerful in the future, but extremely difficult to build today. The competition is not only about who has the most qubits. That is one of the most common misunderstandings. Qubit count matters, but only if the qubits are useful. A large number of unreliable qubits may not outperform a smaller number of cleaner ones. A quantum computer is not judged only by how many quantum bits it contains. It is judged by how well those qubits can be initialized, controlled, connected, protected, and measured. It is judged by how long they maintain coherence. It is judged by how accurately gates can operate. It is judged by whether errors can be corrected before they destroy the computation. In classical computing, bits are stable. They can be copied, stored, checked, and corrected with relative ease. In quantum computing, the information is fragile. A qubit must preserve a delicate quantum state long enough to participate in computation. But quantum states are vulnerable to noise. Heat, vibration, stray electromagnetic fields, imperfect controls, and unwanted interactions with the environment can all corrupt the calculation. This is why error rates are central. A quantum computer with too many errors cannot be trusted to produce useful results. The deeper the computation, the more errors accumulate. For a small demonstration, some noise may be tolerable. For a large, useful algorithm, errors must be controlled with extraordinary precision. This leads to one of the central ideas in the field: fault tolerance. A fault-tolerant quantum computer would use error correction to protect quantum information during long computations. But quantum error correction is difficult because quantum information cannot simply be copied in the ordinary way. The machine must spread information across many physical qubits to create more reliable logical qubits, while avoiding direct measurements that would destroy the quantum state. This means a truly useful machine may require far more physical qubits than the number of logical qubits used in an algorithm. The scale challenge is enormous, but progress is real. Researchers are improving coherence times so qubits can preserve quantum behavior longer. They are improving gate fidelities so operations can be performed with fewer mistakes. They are building better control electronics, better cooling systems, better calibration methods, and better software tools. They are designing quantum algorithms that use fewer resources, tolerate more noise, or target problems where near-term machines might show value. The threshold is not one single device. It is a steady movement from fragile experiments towards scalable quantum systems. That movement is why the race matters even before a fully mature quantum computer exists. Each improvement changes the timeline. A slightly lower error rate may make error correction more realistic. A better qubit architecture may allow larger systems. A new algorithm may reduce the number of qubits needed for a practical task. A better classical quantum hybrid method may make a limited quantum processor useful sooner than expected. The race is not only hardware, it is theory, it is engineering, it is materials science, it is control systems, it is cryogenics, it is software, it is mathematics. It is national strategy. Governments are investing because quantum computing is not just another technology market. It touches security, intelligence, communications, scientific leadership, and economic power. A country that masters scalable quantum computing could gain advantages in cryptography, materials discovery, chemical simulation, logistics, and strategic modeling. Even if the applications take time, the potential is too significant to ignore. Companies are investing because the first practical uses could be commercially valuable. Better materials, better drug candidates, better catalysts, better optimization tools, better financial models. The promises vary in realism, and some are likely overhyped, but the incentives are strong enough to drive massive research programs. Universities are essential because the field is still fundamentally scientific. Many of the hardest questions are not just product development problems, they are open physics and engineering problems. How do we reduce noise? How do we maintain coherence? How do we scale without losing control? How do we design algorithms that exploit quantum structure rather than merely imitate classical methods? Quantum advantage sits at the boundary between proof and usefulness. A demonstration can show that quantum devices are entering a new computational regime. But usefulness requires more. It requires problems people care about. It requires reliability. It requires repeatability. It requires cost and access that make sense. It requires output that can be verified. It requires integration with classical systems. This is why the term quantum supremacy, sometimes used in the past, can be misleading. It suggests a broad victory, as if quantum machines have conquered classical computing. Quantum advantage is more careful. It says that for certain tasks, quantum devices may have an edge, and that edge may grow as the machines improve. The important word is certain. Quantum computers are not expected to accelerate every problem. Many tasks have no known quantum speedup. Some may remain better on classical hardware forever. In the future, most computing may still be classical, with quantum processors used as specialized accelerators for problems where quantum structure matters. That makes the race less like replacing one civilization with another, and more like adding a new kind of engine to the machinery of science and technology. But specialized engines can still change history. A microscope is specialized. A telescope is specialized. A particle accelerator is specialized. None replaces ordinary tools, but each opens a domain that would otherwise remain inaccessible. A useful quantum computer may become a new kind of scientific instrument, one that lets us explore quantum systems by computing with quantum systems. That is the positive vision, but the dangerous vision remains close behind. If quantum machines become powerful enough to run certain cryptographic algorithms at scale, they could undermine public key encryption systems that protect enormous parts of digital life. This is not happening with current noisy devices, but the race toward advantage keeps the concern alive. The same steady progress that excites researchers also pushes security planners to prepare. The danger is not that tomorrow's quantum computer will instantly destroy everything. The danger is that the timeline is uncertain, and large systems take years to change. A threshold can be crossed gradually and still matter. Imagine a mountain range covered in fog. You do not see one sharp line where the old world ends and the new one begins. You see rising ground, better machines, lower noise, more qubits, longer coherence, stronger error correction, more efficient algorithms, more investment, more talent. At some point, the landscape changes. What once seemed impossible becomes difficult. What was difficult becomes practical. What was practical becomes routine. Quantum advantage is part of that rising ground. Some milestones may be symbolic. Some may be useful. Some may be disputed. Some may be surpassed by clever classical methods. But together they show motion. A field that once lived almost entirely in theory is becoming an engineering discipline. A set of quantum effects, once seen mainly as mysteries, is becoming a toolkit. Superposition, entanglement, and interference are no longer only philosophical puzzles. They are resources to be preserved, controlled, and deployed. This is why the race feels so consequential. It is not just a race for faster machines. It is a race to turn fragile quantum behavior into reliable information processing. That transformation is extremely hard. Nature does not give up quantum control easily. The same environment that allows a machine to be built also threatens the delicate states inside it. Every wire, every pulse, every measurement, every vibration, every temperature fluctuation becomes part of the challenge. The quantum computer must be isolated from the world while still being commanded by the world. There is an almost paradoxical engineering beauty in that. To compute with quantum mechanics, you must protect the system from becoming too classical too soon. You must let the strange remain strange long enough to be useful. And then, at the end, you must measure it, forcing the quantum process to deliver a definite result. This is the fragile line researchers are trying to control. The race toward quantum advantage is the race to master that line. No one knows exactly how quickly the field will mature. Some timelines may be too optimistic. Some obstacles may take longer than expected. Some breakthroughs may arrive suddenly. The future is not guaranteed, but the direction is clear enough that the world is paying attention. Quantum computing is moving from possibility toward capability, not in one leap, not with one machine, but through a steady accumulation of progress. More reliable qubits, lower errors, better algorithms, stronger correction, smarter architectures, and deeper understanding of what quantum systems can actually do. The threshold is not a finish line. It is a transition from experiments that prove quantum control is possible to systems that may one day solve problems of real consequence. And that is why the race matters. Because once a machine can reliably do something, no classical computer can practically match. Even if that first task is narrow, the question changes. It is no longer whether quantum computing is possible in principle. It becomes how far the principle can be pushed. The answer may reshape science. It may reshape security. It may reshape the future of information. And it is being built now. One fragile qubit, one corrected error, one careful experiment at a time. The dangerous threshold is not the moment a quantum computer becomes all-powerful. It is the moment it stops being only a scientific demonstration and begins becoming a capability. For decades, quantum computers lived in a strange space between theory and promise. They were real enough for physicists to take seriously, but distant enough for the rest of the world to treat them as speculative. They appeared in papers, laboratories, conference talks, and long-term technology forecasts. They were described as machines that might one day transform computing, but that day always seemed far away, hidden behind engineering problems too difficult to solve quickly. The qubits were too fragile. The errors were too frequent. The systems were too small. The control was too difficult. The dream was powerful, but the machines were limited. That was the safe version of quantum computing, extraordinary in principle, but contained inside the laboratory. A field of deep promise, but not yet a force shaping real-world systems. A threshold becomes dangerous when that balance begins to shift. Not because a single machine suddenly changes the world overnight. Not because every encryption system falls at once. Not because quantum computers instantly become smarter, faster, or more capable than classical computers in every domain. The danger is quieter than that. It begins when the progress becomes steady enough, serious enough, and strategically important enough that governments, companies, scientists, and security agencies can no longer treat quantum computing as a distant theoretical possibility. A dangerous threshold is crossed when a technology starts to matter before it is fully mature. That is the uneasy phase quantum computing is entering. Many current quantum computers are still noisy and limited. They are delicate, experimental systems that require extreme conditions, careful calibration, and sophisticated control. Their qubits lose coherence, errors build up. Their useful calculations are often narrow. Their results can be difficult to verify. They are not yet the large, fault-tolerant machines needed for the most disruptive applications. But the direction of travel matters. The field is no longer only asking whether quantum computation can exist. It is asking how to scale it, how to correct errors, how to connect qubits, how to improve coherence times, how to design better algorithms, how to move from noisy intermediate devices toward machines that can run long, reliable computations. That shift changes everything. In the earliest phase, quantum computing was a question for physics. In the next phase, it becomes a question for infrastructure, for cybersecurity, for medicine, for finance, for materials, for national strategy, for the future of information. This is where the word dangerous becomes appropriate, but only if used carefully. Dangerous does not mean evil. It does not mean apocalyptic. It does not mean quantum computers are machines we should never build. Some of the most powerful technologies in history have been dangerous precisely because they were useful. Electricity was dangerous. Aviation was dangerous. Nuclear physics was dangerous. Artificial intelligence is dangerous in certain contexts. Biotechnology is dangerous in certain contexts. Danger is not the opposite of value. Often, danger appears when value becomes real. Quantum computers could become valuable because they may process certain kinds of information in ways classical machines cannot efficiently match. They could help simulate molecules and materials more naturally, because molecules and materials are quantum systems themselves. They could help design catalysts, batteries, drugs, superconductors, and industrial processes. They could improve certain optimization methods, not by solving every possible problem magically, but by giving new tools for problems with structure that quantum algorithms can exploit. They could reshape science. But the same capability that makes them powerful for discovery can make them disruptive for security. Cryptography is the clearest example. Much of the modern digital world depends on mathematical problems that are extremely hard for classical computers. Some of these problems could become vulnerable to a sufficiently large and fault-tolerant quantum computer. That machine does not yet exist at the required scale. But the risk is serious because encrypted data can be copied now and attacked later. Secrets with a long shelf life, government records, financial data, medical records, intellectual property, identity systems may remain valuable for years or decades. That creates a strange kind of urgency. The threat is not fully here, but the preparation must begin before it arrives. This is what makes thresholds difficult. They are not always visible in real time. A technology can look limited until suddenly it is not. A field can appear slow from the outside while inside it, critical foundations are being laid. Error rates improve. Qubit control becomes cleaner. Algorithms become more efficient. Hardware platforms mature. Engineering problems that once looked impossible become merely hard. Then one day, the question is no longer whether the technology works. It is who controls it, who is prepared for it, and which systems were built assuming it would never arrive. Quantum computing is not alone in this pattern. Many strategic technologies begin as curiosities. Rockets were once experimental machines. Semiconductors were once fragile laboratory devices. Artificial intelligence spent decades moving between hype and disappointment before becoming a central force in technology and economics. The danger rarely appears at the moment of invention. It appears when capability begins to scale. Scaling is the word that matters. A small quantum processor can demonstrate principles. A larger one can test architectures. A more reliable one can run deeper circuits. A fault-tolerant one could perform computations impossible for noisy machines. Each stage changes what is practical. Each stage moves the technology closer to applications that affect the outside world, and progress in quantum computing does not require perfection to matter. A limited quantum machine might help with specialized simulation before it can break major encryption. A hybrid quantum classical approach might improve certain workflows before universal fault-tolerant computing exists. Better quantum sensors, inspired by related quantum technologies, may affect navigation, measurement, and defense even before full-scale quantum computers mature. Quantum networking may open new ways to think about secure communication and distributed quantum systems. The threshold is not one door, it is a corridor. Each step makes the technology less theoretical and more strategic. This is why governments are watching. Quantum computing is not just a scientific prize, it could become a geopolitical asset. A country that develops strong quantum capabilities may gain advantages in secure communication, code breaking, material discovery, pharmaceutical research, logistics, and defense modeling. Even the perception of progress can shape policy, investment, and competition. Companies are watching for a different but related reason. Quantum computing could unlock commercial value in chemistry, optimization, and simulation. Drug development is costly and slow. New materials can shape entire industries. Battery chemistry matters for energy storage. Catalysts matter for manufacturing and climate-related technologies. If quantum computers eventually accelerate even a few of these areas, the economic consequences could be significant. Universities and laboratories are watching because the scientific questions are still deep. How do we build reliable logical qubits? Which physical platform can scale? What error correction codes are most practical? Which algorithms will show real advantage? How do we benchmark progress honestly? How do we avoid mistaking narrow demonstrations for broad usefulness? That last question is important. A responsible discussion of the dangerous threshold must avoid two extremes. The first extreme is hype, the idea that quantum computers are already about to solve every problem, destroy all security, replace all classical machines, and transform civilization instantly. That is not accurate. The machines are not there yet. Many applications remain theoretical. Many barriers remain formidable. The second extreme is dismissal, the idea that because current systems are noisy and limited, quantum computing is not worth worrying about. That is also not accurate. Strategic technologies do not become important only after they are fully mature. Waiting until the capability is undeniable can mean waiting until adaptation is too late. The responsible position is between panic and denial. Quantum computers are not omnipotent, but they are important. They are not ready to break the world, but they may be ready enough to force the world to prepare. The central technical challenge is error correction. Quantum states are fragile. Every interaction with the environment can damage the computation. Unlike classical information, quantum information cannot simply be copied and backed up in the ordinary way. To build a reliable quantum computer, researchers must encode information across multiple physical qubits, detect errors without destroying the computation, and correct them fast enough to maintain the quantum state. This is brutally difficult, but not obviously impossible. If error correction becomes practical at scale, the balance changes. A noisy device becomes a fault-tolerant platform. A short calculation becomes a long one. A scientific demonstration becomes a computing resource. The difference is not cosmetic. It is the difference between a machine that proves quantum behavior and a machine that uses quantum behavior reliably. That is why error rates, coherence times, and control systems matter as much as headline qubit counts. 1,000 poor qubits may not be as useful as fewer high-quality ones. A device that can hold coherence longer, perform gates more accurately, and connect qubits more effectively may represent a more serious step toward real capability than a larger but noisier machine. Quantum progress is not only about size, it is about reliability. And reliability is what turns possibility into power. This is the quiet suspense of the field. The machines today are imperfect, but the engineering curve is active. More researchers are entering the field. More funding is flowing. More architectures are being tested. More software is being written. More standards are being developed. More companies are building roadmaps that stretch beyond laboratory demonstrations. The threshold is not crossed when one dramatic headline appears. It is crossed through accumulation. One better qubit, one lower error rate, one longer coherence time, one improved correction scheme, one more useful algorithm, one more system integrated into real research. At some point, the accumulated progress changes the category of the technology. It becomes strategic. That word carries weight. A strategic capability is not just something interesting. It is something that can alter the behavior of institutions. It influences planning before it fully arrives. It changes what governments fund, what companies protect, what standards bodies prioritize, and what adversaries attempt. Quantum computing is beginning to occupy that role. Even uncertainty becomes strategic. No one knows exactly when large-scale fault-tolerant quantum computers will arrive. Timelines differ. Some forecasts are optimistic, others are cautious. But the uncertainty itself creates pressure, because digital systems are slow to change. Cryptographic transitions can take years. Legacy systems can remain vulnerable long after better methods exist. Long-term data can be stolen before the capability to decrypt it exists. This is how a future capability casts a shadow backward into the present. The machine does not have to exist yet for planning to become urgent. That is one of the most important ideas in this story. The danger is not only what quantum computers can do today. It is what today's systems are assuming about tomorrow. If digital infrastructure is built on the belief that certain problems will remain impractical forever, and quantum computing changes that assumption, then preparation cannot wait for the final proof. The threshold is dangerous because it exposes a mismatch between technological momentum and institutional readiness. Science can advance faster than infrastructure can adapt. Discovery can move faster than policy. Capability can mature faster than security migration. And once a powerful tool exists, it rarely remains confined to the intentions of its inventors. Still, this is not a story of doom. Quantum computing may also become one of the great scientific instruments of the future. It may help us understand nature more deeply, design better materials, simulate molecular systems, and open new areas of knowledge. Its danger comes from its power, and its power may bring enormous benefits. The right response is not fear of the machine, it is seriousness about the threshold. A dangerous threshold is crossed when a technology stops being only a scientific milestone and starts becoming a strategic capability. Quantum computing is approaching that boundary not as a sudden explosion, but as a slow convergence of physics, engineering, mathematics, security, and ambition. The machines remain limited, the challenges remain severe, the future remains uncertain, but the direction is clear enough to matter. Theory is becoming hardware, hardware is becoming systems, systems are becoming capability, and capability, once real, does not stay inside the laboratory. The most famous danger of quantum computing is not that it will make every computer obsolete. It is that it may undermine some of the mathematical foundations that protect the digital world. Every day, invisible systems decide what can be trusted: a bank transfer, a private message, a medical record, a software update, a login session, a government document, a satellite command, a connection between a phone and a server. Modern life depends on the assumption that information can be transmitted, verified, and protected across networks full of strangers. That protection is not based on secrecy alone, it is based on mathematics. Many of the encryption systems used today rely on problems that are easy to perform in one direction, but extremely hard to reverse with a classical computer. This is the quiet genius behind much of modern cryptography. It allows two parties to communicate securely without first sharing every secret in person. It allows digital signatures to prove that a message or software update came from the right source. It allows identity, commerce, and trust to exist across an open internet. Classical computers can, in principle, attack many of these systems, but for strong implementations, the time required is so vast that the attack becomes practically impossible. Not impossible by the laws of physics, not impossible in a philosophical sense, practically impossible. Too slow, too expensive, too large, too unrealistic. Digital security often lives in that gap between possible and practical. Quantum computing threatens to change the size of that gap. A sufficiently powerful, fault-tolerant quantum computer could break some widely used public key encryption systems by solving certain mathematical problems far more efficiently than known classical methods. That sentence needs careful handling. It does not mean every form of encryption collapses. It does not mean every password becomes useless overnight. It does not mean today's noisy quantum machines can suddenly read every private message on Earth. But it does mean that a future quantum computer, if large and reliable enough, could attack parts of the cryptographic infrastructure the modern civilization depends on. That is the cryptographic shock, not instant collapse, a long warning before a possible break. The most vulnerable systems are not usually the simple act of typing a password. Password security depends on many layers: hashing, authentication design, storage practices, user behavior, server security, and sometimes encryption. The quantum threat is more specific. It targets certain public key systems used to exchange keys, establish secure connections, and create digital signatures. Public key cryptography is one of the great inventions of the information age. It allows secure communication between people or machines that have never met. It supports secure web browsing, encrypted messaging protocols, software verification, financial systems, and countless forms of digital trust. It works because certain mathematical operations are easy to verify but hard to reverse. For classical computers, that hardness is the wall. For future quantum computers, parts of that wall may become vulnerable. This is where a quantum algorithm becomes more than a scientific curiosity. It becomes a strategic concern. If a machine can efficiently solve the mathematical problems behind widely deployed cryptographic systems, then the security of those systems changes. Not because the original mathematics was sloppy, not because engineers were careless, but because the assumed attacker model changes. The digital world was built in a pre-quantum era. It assumed the attacker was classical. A powerful enough quantum computer would be a different kind of attacker. That does not mean the entire internet is doomed. Cryptography is not one single lock. It is an ecosystem of methods, protocols, standards, implementations, and operational practices. Some symmetric encryption methods are believed to be more resistant to quantum attack, though they may require stronger parameters. Hash functions can also be adjusted. The biggest concern is public key cryptography of certain widely used kinds. So the threat is narrow in one sense, but enormous in another, because those systems are everywhere. They are built into browsers, servers, operating systems, certificates, banking systems, identity infrastructure, secure messaging, virtual private networks, cloud services, software distribution, and government communications. They are not easy to replace quickly. Cryptographic infrastructure is like plumbing beneath a city. Most people do not see it, but everything depends on it. Changing it takes time, and time is the reason the threat matters now. A powerful quantum computer capable of breaking major public key systems does not exist today. But some data encrypted today may still be valuable years from now. State secrets, diplomatic communications, defense plans, medical records, financial records, intellectual property, biometric databases, legal archives, personal communications, and long-term identity records can remain sensitive for decades. An adversary does not need to decrypt everything immediately. They can steal encrypted data now, store it, wait, and decrypt it later, if quantum machines become powerful enough. This is often called harvest now, decrypt later. It is one of the most realistic near-term risks of the quantum era. The danger is not that every system fails today. The danger is that information captured today may become readable tomorrow. That creates urgency long before the final quantum computer arrives. If a secret must remain secret for 30 years, and a capable quantum computer may arrive within that window, then the threat is already relevant. This is why cybersecurity planners are not waiting for the machine to exist. They are preparing while the machine is still being built. The answer is post-quantum cryptography. Post-quantum cryptography does not mean encryption that uses quantum computers. It means cryptographic methods designed to resist attacks from both classical and quantum computers. These methods are based on different mathematical problems, ones believed to remain hard even for quantum machines. They are meant to replace or supplement vulnerable public key systems before those systems become breakable. This is a global effort. Researchers, standards bodies, governments, companies, and security engineers are working to develop, test, standardize, and deploy quantum-resistant algorithms. The goal is not to panic. The goal is migration. identify vulnerable systems, choose safer replacements, update protocols, test performance, avoid implementation mistakes, protect long-lived data, build a security architecture that can survive the quantum future before that future arrives. That process is difficult because cryptography is not just mathematics, it is implementation. A mathematically strong algorithm can fail if coded poorly. A secure protocol can fail if deployed incorrectly. A standard can take years to reach real systems. Legacy devices may remain in use long after better methods are available. Some systems are hard to update because they are embedded in infrastructure, satellites, industrial control systems, medical devices, or long-term archives. The risk is not only technical, it is logistical. A new cryptographic algorithm can be designed in a paper, but the world cannot upgrade instantly. Banks, hospitals, governments, telecom networks, cloud providers, software vendors, and device manufacturers all move at different speeds. Some systems are modern and flexible. Others are old, fragile, and difficult to replace. Some organizations know exactly what cryptography they use. Others do not. Before a system can be made quantum safe, it must first be found. That is why many experts talk about cryptographic inventory. Organizations need to know where vulnerable algorithms are used, what data needs long-term protection, which systems can be updated, and which dependencies are hidden in software libraries, certificates, hardware modules, and third-party services. This is not glamorous work, but it may be the difference between preparation and exposure. Quantum risk turns cryptography into a question of time. How long must the data remain confidential? How long will migration take? How soon might fault-tolerant quantum machines arrive? How quickly can standards be adopted? How many systems depend on vulnerable public key methods? No one knows the exact timeline. That uncertainty is part of the problem. If quantum computers remain limited for many decades, some preparations may seem early. If progress accelerates, late migration could be dangerous. Security planning cannot rely on perfect foresight. It must handle uncertainty with resilience. This is why the responsible tone is neither alarm nor dismissal. It is seriousness. Quantum computers threaten not all security, but the foundations of some encryption systems that modern digital life depends on. That distinction matters. It prevents the story from becoming exaggerated. A quantum computer will not automatically know your password. It will not instantly unlock every phone. It will not make all cybersecurity meaningless. Attackers will still need access, infrastructure, targets, and methods. Many breaches will still come from ordinary human failures. Weak passwords, phishing, misconfigured servers, stolen credentials, unpatched software, careless design. But quantum computing could remove the hardness assumption behind some of the most important cryptographic tools. And when a foundation changes, everything built on it must be inspected. The deeper issue is trust. Modern digital trust is invisible. Most people do not think about it when opening a banking app, sending a message, downloading an update, or visiting a secure website. The connection either works or it does not. The lock icon appears. The transaction completes. The identity is verified. The software installs. Underneath, cryptography is quietly proving, hiding, authenticating, and protecting. Quantum computing forces a question. What happens when the locks were designed for a world with only classical keys? This is not the first time security has had to evolve. Cryptographic systems have been replaced before. Algorithms once considered safe became outdated. Key sizes increased. Protocols changed. Weak designs were retired. Better attacks appeared. Better defenses followed. Security is never a finished structure. It is a process of adaptation. The quantum transition is different because it is not just a better classical attack. It is a new computational model. That makes the transition more urgent and more uncertain. Post-quantum cryptography must be secure not only against what we know today, but against future advances in both quantum and classical cryptanalysis. Some candidate algorithms may be broken during testing. Some may be too slow or too large for certain systems. Some may require hybrid approaches during migration, combining older methods with newer quantum-resistant ones until confidence grows. This is how serious security work looks: messy, careful, incremental, tested, revised. The goal is not perfection. The goal is to reduce risk before the risk becomes immediate. There is a quiet irony in all of this. Quantum mechanics, the same theory that made modern electronics possible, may eventually challenge the security of the electronic world. The same physics that gave us semiconductors, lasers, magnetic resonance imaging, and the digital age now points toward machines that could force that age to rebuild its locks. Nature is not attacking our systems. Our systems were built with incomplete assumptions about what computation could become. Quantum computing expands that definition. It asks what happens when information is processed not only through classical bits, but through qubits, entanglement, interference, and measurement. It takes principles once confined to atomic physics and turns them into tools. And when tools become powerful, old defenses must be reconsidered. The coming cryptographic shock is not a single day of failure. It is the recognition that preparation has to begin before the threat is fully operational. The future-capable quantum computer may be years away. It may be decades away. Its timeline may be uncertain. But the data being protected today exists now. The systems that need upgrading exist now. The migration effort exists now. The decisions made before the machine arrives may determine how dangerous its arrival becomes. That is why the threshold matters. Not because every secret is exposed today. Because some secrets need to remain protected into the quantum future. Not because quantum computers break all security. Because they threaten key foundations of public key cryptography. Not because panic is useful. Because preparation is necessary. The digital world is built on trust, and trust is built on mathematics that must survive changing machines. Quantum computing does not end that trust by itself, but it demands that trust be rebuilt for a new era of computation. The cryptographic shock, if handled wisely, does not have to become a catastrophe. It can become a transition, a difficult one, a global one, a quiet rebuilding of the locks before the new keys arrive. Quantum computers are powerful in principle, but they are not magic. That distinction matters, because the future of quantum computing is often described in language that moves too quickly from possibility to inevitability. A quantum computer is not a universal supercomputer that automatically beats every classical machine. It is not a device that will replace laptops, phones, servers, or the ordinary digital systems that run most of modern life. It is not a machine that instantly solves every problem simply because it uses quantum mechanics. Quantum computers are different, but different does not always mean better. Their power applies to certain kinds of problems, under certain conditions, with carefully designed algorithms and extremely demanding hardware. In some areas, especially the simulation of quantum systems, the potential is enormous. In cryptography, the long-term implications are serious. In materials, science, and chemistry, the promise is real. But many proposed uses remain theoretical, experimental, or far from practical scale. The danger of exaggerating quantum computing is that it makes the science less clear. The danger of dismissing it is that it makes the future less prepared. The truth is in between. Quantum computers are powerful in principle, but the hard part is turning fragile quantum behavior into reliable computation. A classical computer is not simple, but its information is stable in a way quantum information is not. A classical bit can be stored, copied, checked, refreshed, and corrected with extraordinary reliability. It can represent 0 or 1, and engineers have spent decades learning how to make those states robust. A modern processor contains enormous complexity, but at the logical level, its operations are built from stable, definite values. A quantum computer works with qubits, and qubits are fragile. A qubit must preserve a quantum state long enough to be useful. That state can involve superposition, entanglement, and delicate relationships between possible outcomes. These are the very features that give quantum computing its power, but they are also the features most easily damaged by the surrounding world. The environment is always trying to interfere. Heat can disturb the system. Stray electromagnetic fields can alter it. Vibrations can affect it. Imperfect control pulses can introduce errors. Nearby particles, materials, electronics, and measurement devices can leak information into the environment. The quantum state can lose the coherence that made it useful. This loss of coherence is one of the central challenges of quantum computing. Coherence is not just a technical detail. It is the condition that allows quantum information to behave quantum mechanically. It allows different possibilities in a quantum state to maintain the relationships needed for interference. It allows qubits to remain entangled in controlled ways. It allows a computation to evolve according to the rules the algorithm depends on. When coherence is lost, the computation begins to collapse into ordinary noise. The quantum advantage disappears. The machine becomes less like a powerful quantum processor and more like an extremely delicate system being constantly damaged by its own surroundings. This is why quantum computers often require extreme control. Some systems must be cooled to temperatures near absolute zero. Others require ultra-high vacuum, precise lasers, highly stable electromagnetic fields, or carefully engineered materials. The physical platforms differ, but the problem is shared. Protect quantum information from the environment while still controlling it well enough to compute. That is a difficult balance. A qubit must be isolated from the world, but it must also be manipulated by the world. If it is too isolated, you cannot operate it. If it is too exposed, it decoheres. The entire machine must live in this narrow space between protection and control. And even if coherence is maintained for a while, errors still accumulate. Every quantum operation has some probability of being imperfect. A gate may rotate a qubit slightly too much or too little. A measurement may return an incorrect result. A connection between qubits may introduce unwanted interactions. A pulse may drift. Calibration may change. Noise may enter. The more operations a computation requires, the more opportunities there are for error. For small demonstrations, errors can sometimes be tolerated or mitigated. For large, meaningful algorithms, errors become a war. A useful quantum computer cannot merely perform a few fragile operations. It must perform long sequences of operations while preserving the structure of the computation. It must produce results that can be trusted. It must scale from small experiments to machines with enough reliable qubits to solve problems that matter. This is where quantum error correction becomes essential. But quantum error correction is far harder than classical error correction. In a classical computer, if a bit is important, it can be copied. Multiple copies can be compared. If one bit flips, the system can detect the error and correct it. Classical information can be duplicated freely. Quantum information cannot. An unknown quantum state cannot simply be copied perfectly. This is a fundamental feature of quantum mechanics, not a temporary limitation of engineering. So quantum error correction must work differently. It must protect quantum information by spreading it across multiple physical qubits in a carefully structured way. It must detect signs of error without directly measuring and destroying the information being protected. It must correct the system while preserving the quantum state needed for computation. This is one of the most difficult tasks in modern engineering. A single reliable logical qubit may require many physical qubits. A large fault-tolerant quantum computer may require immense overhead, not just in qubit count, but in control systems, error detection, calibration, connectivity, and stability. The public often hears about the number of qubits in a machine, but the deeper question is how many of those qubits are useful, reliable, and protected well enough to perform long computations. A noisy machine with many qubits may still be limited. A smaller machine with better error rates may be more meaningful. Scale is not only quantity, scale is quality under control. This is why many quantum applications remain far from practical. It is one thing to show that a quantum processor can perform a narrow experimental task. It is another thing to solve a real-world chemistry problem with clear advantage. It is one thing to demonstrate entanglement across qubits. It is another thing to build a fault-tolerant machine capable of breaking widely used encryption systems. It is one thing to publish a promising algorithm. It is another thing to run it on hardware that exists, with enough corrected qubits, low enough errors, and practical runtime. Between theory and deployment lies engineering, and in quantum computing the engineering is severe. This does not mean the field is failing. It means the field is honest when it admits the difficulty. Quantum computing is trying to use some of the most delicate behavior in nature as a computational resource. That was never going to be easy. The same features that make quantum systems powerful also make them fragile. The machine must preserve strangeness long enough to calculate with it, then measure it without losing the answer. That is a remarkable demand. It is also why the hype can be misleading. A quantum computer will not make every algorithm faster. Many problems have no known quantum advantage. Some tasks that sound impressive may still be better handled by classical systems. Search, graphics, databases, ordinary software, operating systems, streaming, office work, and most daily computation will continue to run on classical hardware. Even in a future with powerful quantum processors, they will likely act as specialized accelerators, used for specific tasks where quantum methods offer an edge. The future is not quantum computers replacing classical computers. It is quantum and classical systems working together. A classical computer may prepare the problem, control the quantum processor, interpret the results, correct errors, and handle the broader workflow. The quantum processor may perform the part of the task where quantum structure matters. This hybrid future is less dramatic than the idea of a universal quantum supercomputer, but it is far more realistic. Quantum computers are tools, powerful tools, potentially, but specialized tools. This is especially important in discussions of artificial intelligence. Quantum computing is sometimes presented as if it will automatically create unimaginable AI systems. The reality is more cautious. There are research areas exploring quantum machine learning, optimization, and linear algebra methods, but it is not yet clear where quantum computers will provide practical advantage for mainstream AI. Many AI workloads depend heavily on classical data, memory movement, hardware acceleration, and statistical methods already well served by classical systems. Quantum computing may one day help certain subproblems, but it is not a guaranteed shortcut to artificial general intelligence. Careful science does not turn every possibility into a promise. The same caution applies to optimization. Many real-world optimization problems are hard, and quantum methods may offer advantages for some structured cases. But not every hard optimization problem becomes easy on a quantum computer. Complexity does not vanish. Constraints, noise, data input, output verification, and problem structure still matter. A quantum computer is not a universal answer to every logistical, financial, or strategic challenge. It is a different computational resource, not an oracle. That difference builds trust. The more responsibly quantum computing is described, the more seriously its real potential can be taken. Overhyping the technology creates disappointment and confusion. Understating it creates complacency. The strongest position is clear. Quantum computers are not ready to do many of the dramatic things people fear or hope for, but the scientific path toward those capabilities is real enough to demand preparation. The machines today are limited, but they are improving. Researchers are extending coherence times. They are lowering error rates. They are improving gates, measurements, materials, fabrication, laser control, cryogenic systems, and calibration. They are developing error correction codes and testing them experimentally. They are creating algorithms designed for near-term machines and long-term fault-tolerant systems. They are learning which claims hold up and which do not. Progress in quantum computing is not a straight vertical line. It is a difficult climb. Sometimes a milestone is real, but narrow. Sometimes a breakthrough is technical, but not practical. Sometimes a result is impressive, but later matched by a better classical method. Sometimes a hardware platform makes progress in one metric while struggling in another. This is how emerging science often looks from the inside: uneven, careful, and full of corrections. That does not make it less important. It makes it more real. A mature quantum computer must do more than exist. It must compute reliably. It must scale without losing control. It must correct errors faster than they spread. It must run algorithms whose results can be validated. It must offer enough advantage to justify its complexity, and it must fit into a world where classical computers are already extraordinarily powerful. That is the standard, and meeting it is hard. Still, the reason the field continues is that the reward could be profound. A reliable quantum computer could simulate molecules and materials with a naturalness classical machines struggle to match. It could help explore physics, chemistry, and complex quantum systems. It could change certain security assumptions. It could become a new scientific instrument for the quantum world. But the path from principle to practice is not automatic. Nature does not hand us computation just because the equations allow it. A machine must be built, controlled, protected, corrected, scaled, verified. This is the hard reality behind the quantum threshold. The future of quantum computing depends not only on how strange quantum mechanics is, but on whether humans can engineer that strangeness into stability. And that is where the true challenge lies. Quantum computers are powerful in principle, but the hard part is turning fragile quantum behavior into reliable computation. Until that is done at scale, many of the most dramatic applications remain ahead of us. not behind us. The promise is real. The danger is real, but so are the limitations. The threshold has not erased the difficulty. It has made the difficulty matter more. The right response to a dangerous threshold is not panic. It is preparation. That distinction matters because quantum computing often enters public conversation through extremes. In one version, it is a miracle machine that will solve every problem. In another, it is a threat that will instantly break the digital world. Both pictures are too simple. The real situation is more careful, more technical, and more important. Quantum computers are advancing, but large fault-tolerant machines capable of the most disruptive cryptographic attacks are not here yet. At the same time, waiting until they are here would be a mistake. The systems that protect modern digital life are too large, too old, too interconnected, and too slow to upgrade overnight. Security is not something a civilization can replace at the last second. It has to be rebuilt before the crisis arrives. That is why governments, standards agencies, cybersecurity teams, research institutions, and technology companies are already preparing. Their work is not dramatic in the way a breakthrough headline is dramatic. It happens in committees, laboratories, audits, software updates, migration plans, security reviews, and long documents that most people will never read. But this quiet work may decide how disruptive the quantum transition becomes. The goal is simple to say and difficult to execute. Make digital systems safer before quantum computers become powerful enough to threaten them. The central effort is post-quantum cryptography. Post-quantum cryptography means encryption and digital signature methods designed to resist attacks from both classical and quantum computers. It does not require a quantum computer to use. It does not mean quantum communication. It means new mathematical foundations for security, chosen because they are believed to remain hard even in a future where attackers may have quantum capabilities. This is one of the most urgent areas of preparation. Many public key systems in use today rely on mathematical problems that are extremely difficult for classical computers. A sufficiently powerful quantum computer could change that. So the world needs replacement systems, algorithms that can protect secure connections, verify identities, sign software, protect financial transactions, and preserve confidential information in a post-quantum world. But choosing new algorithms is not like choosing a new password. Cryptographic standards must be tested carefully. Researchers need to examine the mathematics, search for weaknesses, compare performance, study implementation risks, and evaluate whether the algorithm can run efficiently across real devices and networks. A method that looks strong in theory can fail if implemented poorly. A method that is secure but too slow or too large may be hard to deploy in constrained systems. A method that works well for servers may not work well for satellites, sensors, medical devices, or older infrastructure. The problem is not only cryptography, it is migration. The digital world is full of hidden dependencies. Cryptography lives in web browsers, cloud platforms, banking systems, messaging apps, government networks, identity systems, software updates, secure chips, industrial control systems, medical databases, satellites, military communications, and long-term archives. It is inside devices that may remain in service for decades. It is buried in protocols, certificates, hardware modules, libraries, and systems that were never designed with quantum migration in mind. To prepare, organizations first have to know what they are using. That sounds simple. It is not. A bank may have thousands of systems, some modern, some legacy, some maintained internally, some dependent on third-party vendors. A hospital may protect patient records across electronic health platforms, insurance systems, medical devices, cloud backups, imaging tools, and external partners. A government agency may store records that must remain confidential for decades. A satellite system may use hardware that cannot easily be physically upgraded once deployed. Before anything can be made quantum safe, it must be found, understood, prioritized, and replaced carefully. This is why cryptographic inventory matters. Security teams need to map where vulnerable public key algorithms are used, what data they protect, how long that data must remain secret, and which systems can be upgraded first. They need to identify high-risk areas, long-lived secrets, critical infrastructure, sensitive communications, identity systems, and systems that are difficult to patch. The quantum threat is not equal everywhere. Some data only needs to be confidential for a short time. Some needs protection for years. Some needs protection for decades. The longer the required secrecy, the more urgent the migration becomes. This is especially important because of the harvest now, decrypt later problem. Encrypted data can be stolen today, stored, and decrypted later if quantum machines become capable enough. That means preparation is not about a distant future alone. For long-lived data, the future already matters. Banks cannot wait until a powerful quantum computer exists if the financial infrastructure takes years to update. Hospitals cannot wait if medical records must remain private across a lifetime. Governments cannot wait if diplomatic, military, or intelligence data must stay secret for decades. Satellites cannot wait if their communication systems are difficult to replace after launch. Infrastructure operators cannot wait if old control systems cannot be patched quickly. The timeline of quantum hardware is uncertain. The timeline of institutional change is slow. That mismatch is the danger. Preparation also includes risk assessment. Not every system needs to move at the same speed. Not every organization faces the same exposure. A public website, a classified archive, a payment system, a satellite command link, and a hospital database all have different threat models. Good preparation means understanding which risks are immediate, which are long-term, and which are theoretical. Panic treats every risk as equal. Preparation does not. Preparation sorts, measures, prioritizes, and acts. Standards agencies play a crucial role because the world needs trusted, tested, interoperable methods. If every organization invented its own cryptographic solution, the result would likely be chaos. Security depends on public scrutiny, shared standards, and broad confidence. The mathematics must be challenged by experts before it protects critical systems. The implementation must be tested before it becomes infrastructure. This is why standardization is slow by design. It is meant to be careful. A rushed cryptographic standard can create more danger than it solves. A poorly tested algorithm may fail. A hasty migration may introduce bugs. A system may become quantum resistant in one layer while remaining vulnerable in another. Real security is not a label. It is an ecosystem. Post-quantum migration may also use hybrid approaches during the transition. In some cases, systems may combine existing methods with post-quantum methods, so security does not depend entirely on a single new algorithm before confidence is fully mature. This can help manage uncertainty, but it also adds complexity. More complexity can mean more opportunities for mistakes, so deployment has to be engineered with care. The work is not glamorous, but it is essential. At the same time, preparation is not limited to cryptography. Research institutions are also developing quantum networking, quantum communication, and quantum-safe infrastructure. Quantum networking explores ways to connect quantum systems, distribute quantum states, and eventually support new forms of secure communication or distributed quantum computation. These technologies are still developing, and they do not replace the need for post-quantum cryptography, but they are part of the broader preparation landscape. Governments are investing because quantum technology has strategic consequences. A nation that develops advanced quantum computers may gain scientific, economic, and intelligence advantages. A nation that fails to protect its infrastructure may become vulnerable. This is why quantum readiness has become a policy issue, not just a research topic. It touches national security, economic resilience, and technological sovereignty. Companies are preparing because trust is part of business. A financial institution, cloud provider, software company, or healthcare platform cannot simply tell customers that quantum risk is someone else's problem. If the systems that protect identity, transactions, and confidential data become outdated, trust erodes, and once trust is lost, it is hard to rebuild. Cybersecurity teams are preparing because they understand a basic truth. Migration is always harder than theory. In theory, you replace old algorithms with new ones. In practice, systems break, vendors lag, legacy devices resist updates, certificates expire, performance changes, compatibility issues appear, users make mistakes, attackers look for the weak points created during the transition. The safest algorithm in the world does not help if it is deployed incorrectly or only partially. So preparation must include testing, training, monitoring, and long-term planning. It must include people, not just mathematics. Engineers need to know how to implement new standards. Security teams need tools to detect outdated cryptography. Executives need to understand why money must be spent before the disaster is visible. Governments need timelines and requirements that match the seriousness of the risk without creating unnecessary panic. Researchers need support to keep testing assumptions. This is the responsible path, not fear, not complacency, readiness. There is also a scientific humility in this preparation. No one knows exactly when large-scale, fault-tolerant quantum computers will arrive. Predictions vary. Some are optimistic, some are cautious. Breakthroughs can accelerate progress. Engineering obstacles can slow it down. A responsible plan must live with uncertainty rather than pretend it can eliminate it. The question is not whether we can predict the exact date. The question is whether critical systems can survive a range of plausible futures. That is how serious risk management works. You do not wait for certainty before reinforcing a bridge. You do not wait for a fire before designing exits. You do not wait for a cyber attack before patching a known weakness. And you do not wait for a cryptographically relevant quantum computer before beginning a migration that may take years. The dangerous threshold demands a different sense of time. Quantum computers may still be limited today, but the systems they threaten are already deployed. The data they may one day expose may already be stored. The infrastructure that must migrate is already complex. The organizations that must act are already slow. Preparation has to begin while the threat is still forming. This is not unusual in science and technology. Many of the most important responses happen before the public sees the danger clearly. Engineers strengthen systems before failure. Epidemiologists track patterns before outbreaks spread. Astronomers map near-Earth objects before impact becomes likely. Climate scientists model change before every consequence is visible. Cybersecurity works the same way. The point is to act before the emergency becomes irreversible. Quantum readiness is a form of scientific maturity. It means accepting that power is coming with uncertainty. It means building defenses without pretending to know the exact timeline. It means recognizing that the future of computation may be different enough to require action now. And it means refusing the false comfort of both extremes, panic and denial. The preparation already underway is one of the reasons the quantum threat does not have to become a disaster. If systems migrate in time, if standards are tested well, if organizations inventory their cryptography, if long-lived data is protected, if critical infrastructure is prioritized, then the arrival of powerful quantum computers can be managed. It may still be disruptive. It may still be expensive. It may still require years of work. But disruption is not the same as collapse. The future is not fixed. Preparation changes outcomes. That is the quiet message beneath the technical details. Quantum computing may cross dangerous thresholds, but society is not helpless. The same scientific culture that builds quantum machines can also build defenses against their risks. The same mathematics that reveals vulnerabilities can create stronger systems. The same global attention that drives competition can also drive standards, cooperation, and resilience. The right response to a dangerous threshold is not panic, it is preparation, because panic arrives too late and sees only fear. Preparation starts early and turns uncertainty into action. It audits the hidden systems. It updates the old locks. It protects secrets before they are exposed. It gives banks, hospitals, governments, satellites, infrastructure, and archives time to survive a world where quantum computation is no longer only theoretical. A powerful quantum computer may not exist yet at the scale needed to break today's most important systems, but the work of living safely in that future has already begun. Quantum computing represents a new relationship with information. For most of modern history, computation has been built on certainty. A bit is 0 or 1. A circuit opens or closes. A signal is high or low. A memory cell stores a definite value. The digital world became powerful because it learned to make information stable, repeatable, and controllable. From that stability came software, networks, encryption, finance, medicine, satellites, artificial intelligence, and the invisible infrastructure of modern life. But quantum computing begins somewhere less familiar. It begins with information before it becomes fully definite. A qubit is not merely a smaller bit. It is a quantum system, and quantum systems do not behave like ordinary switches. They can exist in structured combinations of possible outcomes. They can become entangled, so that the full state of a system belongs not to isolated parts, but to relationships. They can interfere, allowing some possible paths to reinforce and others to cancel. They can evolve according to rules that are precise, but not classical. A quantum computer tries to use that strangeness as a resource, not only to observe the quantum world, but to compute with it. That is the turning point. For over a century, quantum mechanics has told us that nature is stranger than everyday experience. Particles behave in ways that are not like tiny objects. Measurement changes what can be known. Probabilities are not merely ignorance in the ordinary sense. Entanglement creates correlations that no classical picture can fully explain. These ideas were once treated as deep puzzles about reality. They still are, but now they are also becoming engineering principles. Superposition becomes a way to encode information. Entanglement becomes a way to connect information. Interference becomes a way to shape information. Measurement becomes the moment the answer is pulled from a carefully prepared quantum process. This is why quantum computing feels so powerful and so uncertain. It is not just a new machine. It is a new way of asking nature to participate in computation. A classical computer manipulates bits according to rules humans designed from classical logic. A quantum computer manipulates quantum states according to rules nature already uses at the deepest levels of matter. In that sense, quantum computing is not an escape from physics. It is a deeper surrender to physics. But power is arriving before certainty. That is what makes the threshold dangerous. We do not yet know exactly how fast quantum computers will scale. We do not know which hardware platforms will become dominant, or whether several will coexist for different purposes. We do not know how quickly error correction will become practical at large scale. We do not know which algorithms will matter most outside the laboratory. We do not know how soon quantum machines will become useful for chemistry, materials, optimization, artificial intelligence, or cryptography in ways that clearly outperform classical systems. The future is visible only in outline, and yet the direction is serious enough to change decisions now. This is the difficult space modern civilization has entered, a space between promise and proof, between risk and readiness, between fragile prototypes and future capability. Quantum computers are still limited. They are noisy. They are difficult to build. Many proposed applications remain far from practical. A large, reliable, fault-tolerant quantum computer is still one of the hardest engineering challenges in technology. But the fact that it is hard does not mean it can be ignored. History rarely waits until a technology is mature before it begins reshaping the world around it. Nuclear physics changed politics before every reactor was built. Spaceflight changed strategy before humans walked on the moon. Artificial intelligence changed economies before anyone fully understood its limits. The early stages of a technology can alter planning, investment, fear, and competition long before the final form arrives. Quantum computing is moving through that same uncertain zone. The machines are not yet fully capable of the most dramatic tasks people imagine, but the possibility has become concrete enough for governments to prepare, companies to invest, standards agencies to act, and cybersecurity teams to rethink the foundations of digital trust. That is not panic, that is recognition. The most immediate concern is not that quantum computers will replace every computer or instantly solve every problem. They will not. The concern is that they may eventually solve certain problems too well. Some encryption systems depend on mathematical difficulty that classical computers cannot realistically overcome. A sufficiently powerful quantum computer could change that assumption. And because sensitive data can be stolen now and decrypted later, preparation has to begin before the final machine exists. This is what makes the danger unusual. The threat is partly future, but the vulnerable data may already exist. A diplomatic record, a medical archive, a financial secret, a military communication, a corporate design, a long-term identity system, a private message meant to remain private for decades. These do not wait safely outside time. They can be copied, stored, and held until the tools to read them become available. Quantum computing turns the future into a pressure on the present. And yet, this story is not only about danger. To see quantum computers only as a threat is to miss their deeper promise. A reliable quantum computer could help us simulate molecules and materials with a realism classical machines struggle to reach. It could help reveal new chemistry, new catalysts, new batteries, new medicines, or new materials whose behavior depends on quantum interactions too complex to model easily today. It could become a scientific instrument for understanding nature by using nature's own rules. That possibility is profound. The same quantum logic that threatens parts of cybersecurity could also unlock deeper knowledge of matter. The same entanglement that makes quantum systems difficult to simulate classically could become a tool for exploring physics. The same interference that makes quantum algorithms strange could help search through structured problems more efficiently. This is the dual nature of powerful technology. The tool is not simply good or bad, it expands what can be done. And once possibility expands, responsibility must expand with it. That is why the threshold demands maturity. It asks scientists to be honest about limitations. It asks companies not to exaggerate every milestone. It asks governments to prepare without fear-mongering. It asks cybersecurity teams to migrate systems before urgency becomes crisis. It asks the public to understand that quantum computing is neither magic nor myth. It is a difficult, emerging technology built from real physics, with real limits and real consequences. The most dangerous misunderstanding would be certainty. Certainty that quantum computers will change everything tomorrow, or certainty that they will never matter. Both are too simple. The honest position is harder. Quantum computers may become transformative, but the path is uncertain. They may arrive slowly, then suddenly. They may first matter in narrow scientific domains, then later in security. They may surprise us with applications no one has yet predicted. They may also fall short of some current expectations. Their future will be shaped by physics, engineering, economics, policy, and time. We do not know enough to be certain, but we know enough to prepare. That is the calm lesson beneath the tension. A dangerous threshold does not require fear, it requires attention. It requires systems that can adapt before they break. It requires cryptography that can survive a new kind of attacker. It requires research that separates hype from progress. It requires international awareness, technical standards, and long-term thinking. Quantum computing is a reminder that information is physical. It is not an abstract ghost floating outside the universe. Information must be stored, processed, protected, transmitted, measured, and transformed by physical systems. Classical computers use transistors and electricity. Quantum computers use qubits and controlled quantum states. The rules of nature decide what computation can be. That idea reaches beyond technology. It changes the meaning of intelligence, security, and knowledge. Every civilization builds its tools from the physical laws it understands. Fire came from chemistry. Engines came from thermodynamics. Electronics came from electromagnetism and quantum physics. Digital computing came from logic made physical in circuits. Quantum computing is the next step in that long story. Not just using matter to compute, but using the quantum structure beneath matter. That is why it feels unsettling. It brings the deepest layer of reality closer to human intention. For decades, quantum mechanics seemed like something we studied from the outside. Now we are trying to build machines that hold quantum states, protect them, entangle them, guide them, and measure them for answers. We are learning to turn uncertainty into computation, not by removing uncertainty, but by shaping it. There is a quiet power in that, and there is risk. Power without certainty is always dangerous, not because it is evil, but because it moves faster than understanding, faster than policy, faster than infrastructure, and sometimes faster than wisdom. Quantum computing may open doors before we fully know what is behind them. It may solve problems before society has prepared for the consequences. It may create advantages that are unevenly distributed. It may challenge systems built on assumptions that once seemed permanent. The answer is not to close the door. The answer is to walk through it carefully. Quantum computers are not dangerous because they are mysterious. They are dangerous because they may turn the deepest rules of nature into a tool powerful enough to challenge the digital world built before them. And that is why this threshold matters. Not because the future is doomed, not because the machines are magical, but because a new kind of computation is becoming real, and the world that depends on information must now decide how wisely it will adapt. Good night, and see you in the next video.